Hi everyone. I'm going to go over number 22 from Problems and Exercises from chapter 7. There were some questions about this one. I think that many of those questions might have actually been about the test prep one, but I decided to go over this one just because I think it's a good opportunity to talk about how to solve these conservation of energy problems as a whole. Because there is one approach that you can use in pretty much all the problems, and I think it's a good idea to kind of break it down and look at that. So our formula that we're going to use is potential energy plus, actually, I'm just going to use, I think your textbook does PE and KE. I know that some of the resources are different, but I am going to use that as well. So potential energy initial plus kinetic energy initial plus whatever else is doing work is going to equal our potential energy at the end plus our kinetic energy at the end plus any heat that we have. Right, so then once we have this written down, we can kind of break down what exactly we have. So first I like to make this into a little bit of a bigger thing. So if we look at our potential energy, we know that we can have potential energy that's gravitational, and we can have potential energy that is from a spring, and that'll be at the end too. So I'm going to kind of put that on there. And then other than that, now we have these, we can kind of break everything up into pieces. Okay, so we can break these up into what they are, and I like to start every problem this way, just because then you can go through and look and see what you actually have playing a role in that problem. So for our first one, we have mg. For our first gravitational potential energy, it's going to be mg times our initial y position, plus our, if we have any spring, it's going to be in the form of 1/2 the spring constant times that initial x position squared. And then our kinetic energy is going to be 1/2 mv initial squared, plus our other work. And that's going to be equal to our same kind of stuff over here. So mgy at the end plus 1/2 kx at the end plus 1/2 mv at the end plus our heat. Okay, so then we can read our question, and so this is where we would start for any problem, right? We write out this whole thing, and then we can break it down and look at the question. So this one says that we have a really big subway train that's brought to a stop from a speed of 0.5 meters per second in 0.4 meters by a large spring bumper at the end of the track. What is the force constant of the spring? So it looks like we have a ton of kinetic energy initially turning into a bunch of potential energy in the form of a spring, right? So for the beginning, it looks like we're going to have this. So we're going to have 1/2 mvi squared equals, and then it's the spring that's stopping it. So 1/2 kxf squared. And all this other stuff either isn't playing a role in the situation, or it's just not involved in this problem. And so they asked us to find the spring constant. So we would just solve this for k. So I'm going to divide by 1/2 xf squared. And so my halves are going to cancel, and I'm just going to be left with k equals mvi squared divided by xf squared. Okay, so then we can just plug this in with everything that's given in the problem. Now see how I'm solving this with all variables? That's a really important thing that I want you to make sure that you're doing, because it came up on someone's review that there's not a lot of numbers on the test. And that's really true. And that is a difference between our practice problems and our test questions. But if you're practicing like this, where all you're doing is plugging everything in at the end, then it's totally fine and you're gonna be okay. If you want, you can always change these problems. So you could say a subway train with a mass m is brought to a stop from a speed vi, right? And then you can just change that, take the numbers out of the problems if you want to get that additional practice that looks like that. But what I try to do is just like try to plug in the numbers at the very end, so that I don't get into trouble with that. And that's what I ideally would like all of you to be doing too. So K is our mass, which is 5 times 10 to the 5th times our initial velocity, which is 0.5 squared, divided by our spring gets compressed, it says, by 0.4 meters. So that's going to be how far it is from its starting point. So our XF is going to be 0.4, and that's going to be squared. So we're going to get 5 to the 5th times 0.5 squared divided by 0.4 squared. And that's going to give us 7.81. And this is 1, 2, 3, 4, 5 times 10 to the 5th newtons per meter. Now I didn't do the analysis of the units on there. I just left them off with my calculation. Check in with me if you're having trouble with that, because that is a really important part. I don't know why I didn't do it, but if you're not able to do it with the unit analysis, then let me know and I can go through that with you, because I do want you to know that. All right, I hope this one helps. And remember, this is the approach that you can use for every one of these problems, whether there's heat and non-conservative forces or not. So keep that in mind as you are working. Thank you.